Here's a question. You flip a fair coin 100 times. What's the probability you get exactly 50 heads? Most people say something close to a half, because 50 is the expected value. The real answer is about 8%. Now try a harder one. What's the probability the running average never crosses 1/2 after the 10th flip? That one has an exact answer too, but deriving it is a genuinely unpleasant afternoon. Or you could just flip the coin 100,000 times and count. That's what this series is about. Welcome to Probability Executed. Last series we did this on paper, sample spaces, expectation, the law of large numbers. This series we make the same ideas run. Today, why simulation is a legitimate way to answer probability questions rather than a cop-out, how to generate 10,000 random outcomes without writing a loop, how to watch a theorem prove itself on screen, and the one mistake that quietly invalidates almost everyone's first simulation. First, let's be fair to the paper method, because it's genuinely better when it works. For a single fair coin, the probability of heads is 1/2. For the number of heads in 100 flips, we have the binomial distribution, an exact formula, no computation needed. Analytical answers are exact. They hold for every input at once, and they tell you why the answer is what it is. A simulation gives you a number for one specific case, and it's slightly wrong. So the paper method wins whenever it's available. The problem is how quickly it stops being available. Change the question very slightly. Suppose you keep flipping until you've seen 3 heads in a row, and you want the distribution of how long that takes. Or you want the chance a random walk stays positive the entire time, or your coin's bias itself drifts. Every one of those is either a hard derivation or has no closed form at all. Real problems don't arrive in textbook shape. Simulation doesn't care what shape they arrive in. So here's the setup, and it's smaller than you'd expect. One import. NumPy gives us a random number generator, and we create it with an explicit seed. That seed matters, and we'll come back to it. This generator object is the modern way to do this, by the way. If you've seen tutorials calling numpy.random.seed directly, that's the legacy interface, and it uses hidden global state that makes results hard to reproduce reliably. And here's the line that does the actual work. Integers 0 to 2, size 10,000. That generates all 10,000 coin flips in one call as a single array. Notice what isn't here. There's no for loop. This is what vectorization means. The looping still happens, but it happens inside compiled C code rather than in the Python interpreter, which is roughly 50 times faster. Writing the loop yourself is the single most common thing that makes a simulation too slow to be useful. Now we check it against the theory. Taking the mean of an array of zeros and ones gives us the proportion of ones, which is our proportion of heads. Run it, and we get 0.4961. Theory said 0.5. We're off by about 4 thousandths from 10,000 flips. That gap is not an error, it's the point. A simulation is an estimate, and estimates have a precision you can predict, which we'll get to. But a single number hides the interesting part. Let's compute the running average after every single flip, using cumulative sum divided by the flip count. Now plot it, and there it is. At the left, with only a handful of flips, the line swings violently, 60%, 30%. Then it tightens, and by a few thousand flips it's locked onto 1/2 and stays there. That is the law of large numbers, not stated, but happening. Now watch what happens when we turn it up, because the way the error shrinks is the most useful fact in this entire episode. 100 flips gives you roughly 5 percentage points of error. 10,000 gives you 0.5 point. 1,000,000 gives you 0.05. Every time you multiply the sample size by 100, the error drops by 10. Error falls with the square root of n. That's why the first 3 decimal places are cheap, and the 4th one is brutally expensive. Which gives you a genuinely practical rule. Before you run a simulation, decide what precision you need, then work out n from it. If you need 2 decimal places, you need on the order of 10,000 trials. 3 decimals, a million. Running 10 million trials to report a number you'll round to 2 digits is pure waste, and running 1,000 to report 4 digits is worse, because it looks precise and isn't. Now the honest caveat, and it's the mistake I promised at the start. Look at that seed again. With a fixed seed, your results are reproducible, which is good. But it also means you're looking at exactly one random universe. If you tune anything, like a threshold, a parameter, until the numbers look right on seed 42, you have not found a real effect. You've fitted to noise. Develop on a fixed seed. Validate on several different ones. Report the spread, not just the single number you happen to like. So, one sentence. If you can describe a random process precisely enough to code it, you can measure its behavior without ever solving it. 6 lines of NumPy, just verified a theorem experimentally. Next episode, we hit the first wall where simulation alone won't save you. There are almost 14 million possible lottery tickets, and if you try to generate them all to count them, you'll be waiting a while. Counting, when the things are too numerous to count.